Okay, so let us start our class. Okay, so we'll start our class now. Good evening, everyone. So today we are in live session 2. Today we will be solving week 2 assignment. The course is Petroleum Reservoir Engineering. The course tutor is Dr. Pankaj Tiwari. He is from Department of Chemical Engineering, IIT Guwahati. And I am the TA for the course. I am a Prime Minister Research Fellow and I am also from IIT Guwahati. So, okay. So let us first get a quick revision of week 2 contents. First is reservoir. The topic is reservoir rock and fluid properties. As we have done in the earlier class, first will be go through this API gravity. I have already told you about API gravity in the last class, and also you have done all this in your class, so I won't go into the detail. Today we will be solving some of the numericals, so we won't go much into the theory part. Just some basics so that you can which will help you with the numericals. So for API gravity, the formula is degree API equal to 141.5 divided by specific gravity at 60 degree Fahrenheit minus 131.5. It is specific gravity of the crude oil. So if the API gravity of the crude oil is from 0 degree to 20 degree, then it is called heavy crude. If it is from 20 to 30 degree, it is called medium crude, and if it is more than 30 degree, it is called lighter crude. Means the API gravity is inversely proportional to the means density of the crude. You can write the formula degree API equal to 141.5 divided by specific gravity at 60 degree Fahrenheit minus 131.5. These measurements are taken at atmospheric pressure temperature, that is 60 degree Fahrenheit and 1 atm pressure. Write the formula. Okay, so next we'll go to next slide. What are the types of reservoir? Types of reservoir are oil reservoir and gas reservoir. For oil reservoir, the reservoir temperature is less than critical temperature. For gas reservoir, the reservoir temperature is more than critical temperature. This is a basic definition by which we can distinguish between the oil reservoir and gas reservoir. Then again, there are types of oil reservoir. There is black oil reservoir, there is low shrinkage oil reservoir, then there is volatile oil reservoir, then there is near critical oil reservoir. Again, there are types of gas reservoir, that is dry gas reservoir, wet gas reservoir, and retrograde condensate reservoir. For black oil reservoir, the GOR, gas oil ratio, I have already told you what is gas oil ratio in my previous class. So the gas oil ratio is 200 to 700 SCF per STB. For low shrinkage oil reservoir, the GOR is less than 200 SCF per STB. For volatile oil reservoir, the GOR is 2000 to 3200 SCF per STB. For near critical oil reservoir, the GOR is more than 3000 SCF per STB. For the gas reservoirs, for dry gas reservoir, the gas oil ratio is more than 100,000 SCF per STB. For wet gas reservoir, it is between 60,000 to 100,000 SCF per STB. And for retrograde condensate reservoir, the GOR is ranging from 8,000 to 70,000 SCF per STB. You can note this down. Is the slides visible, sir?
Yes, sir, it is visible.
Okay. So let me go to the next slide. See, in today's class, I have mainly given the formulas that we'll be using to solve the numerical. I have not gone into the detail of this theoretical part because there are numericals to solve and we'll need time for that. So for the gas law, there is ideal gas law, then there is real gas law. For ideal gas law, the formula is PV equal to nRT. For real gas law, the formula is PV equal to Z and RT. So in case of real gas law, R value can be taken as 10.73 psi feet cube divided by mole Rankine, degree Rankine. So the standard pressure and temperature is 14.7 psi and the temperature is 520 degree Rankine. So this pressure and temperature was used to find the value of R, the constant R. Next is gas specific gravity. To find out the gas specific gravity, it is equal to apparent molecular weight of the gas divided by 28.97. 28.97 is the molecular weight of air. You should remember that the molecular weight of air is 28.97. Then there is gas density. The formula is molecular weight into pressure divided by ZRT. Then there is gas viscosity. There are two types of gas viscosity: the dynamic viscosity and the kinematic viscosity. The viscosity that we measured that we use in our petroleum industry is the dynamic viscosity. Its unit is centipoise. Again, next, for measuring the apparent molecular weight, the formula is summation of limit I to n, and it is product of yi into molecular weight of I. I is the ith component and y is the mole fraction of the ith component. So if there are three types, means if in the gas there is carbon dioxide, then there is methane CH4, then there is ethane, butane, then we'll take the molecular weight of each of this component and multiply it with the mole fraction of that component, and then we'll add all these components. Means we'll multiply the mole fraction into molecular weight of each component, then we'll add this one with the mole fraction and molecular weight of the other component present in the atmosphere or present in the gas that we'll be dealing with. Next is gas compressibility factor. Its formula is Z equal to volume actual by volume ideal. So gas compressibility factor is the volume of gas that is actually present and volume of the ideal gas. Write down this formula, then we can go to the next slides. What happened to others? Not why there is so less attendance today? Is your classmates also attending this course, or is it you from your class, Syed?
There are three more people except than me, sir.
Okay, you can
I
message
don't
them.
know. They are not taking up calls.
Okay, okay, no problem. So you note down this formula, then we can go to the next slide. If you find 2 hours very exhausting, we can take some rest after 1 hour, 5 to 10 minutes break. Okay, let's go to the next slide. Next formula is for formation volume factor, Bg. It is denoted by Bg. The formula is 0.0238 ZT by P, reservoir feet cube per SCF. It can be also written as 0.00504 ZT by P, reservoir barrel per SCF. The difference between the two formulas is that the first one is for reservoir when we are making the calculation at reservoir condition, that is at high pressure temperature, and next when we are making the equation at the sorry, the first formula is at the reservoir temperature pressure, but when you are calculating at feet cube per SCF, and the next one is when we are calculating in barrel per SCF. Next is the gas compressibility factor. It is actually the inverse of formation volume factor. It is I by 1 by Bg. So the formula is 35.3 pressure by ZT SCF per reservoir feet cube. It can also be written as 198.32 pressure by ZT SCF per reservoir barrel. This gas compressibility, the formula is 1 by P minus 1 by Z del Z by del P. And for the initial gas in place, the formula is GI, that is gas initial, equal to 43560 area into height into porosity into saturation of gas divided by formation volume factor of gas. And the unit is SCF, standard cubic feet. You can write down the formula. In initial gas in place, the area is in feet cube, height is in feet, porosity is in decimal, and saturation is also in decimal. Bg we can find out from the above formula. So write down this formula, then we can go to the next slide. If you have any question, anything you want to ask regarding the concept, see, in this class I am not going into the concept because there are numericals that we'll be solving today. So if you want to ask, have any doubt about any concept, you can unmute yourself and ask me. Okay, let me go to the next slide. Next, we'll be coming to oil properties. For oil density, the formula is rho equal to 62.4 specific gravity of oil plus 0.0136. RS is the solution gas ratio, then specific gravity of gas divided by B naught. B naught is the oil formation volume factor. The formula for oil formation volume factor is same as uh, gas formation volume factor. It is volume of oil at pressure temperature and volume of oil at standard pressure temperature. B naught is the volume of oil at the pressure temperature that we will be calculating at, divided by the volume of oil at standard pressure and temperature. Next is specific gravity of oil. This can be found from the API gravity. Degree API equal to 141.5 divided by specific gravity minus 131.5 131.5. For oil compressibility, the formula is C naught equal to minus 1 by V by del P at isothermal condition. And the laboratory tests that are performed for finding all these characteristics of natural gas and the crude oil are some are primary tests, then there is routine test, then there is special tests. I won't go into the detail. I will be going to the numerical next. Write down the formulas. We will be needing these formulas while we will be solving the numericals. There are also many correlations that are used in petroleum engineering. There for finding the oil density, there are correlations. For finding the viscosity, oil viscosity, there are many correlations. Correlations are given by uh, different scientists based on the experiments they have performed. Since there are many correlations, I haven't mentioned them in my slides. You have already studied them in your regular NPTEL class. So if any correlations are there, I will, while solving the numerical, if you are using any correlations, I will be writing down the equations at that time directly. So if you have written the formulas, we can go to the numericals directly. First question is, a gas well is producing gas with an apparent molecular weight of 20 at a rate of 1.5 mmscf per day. Calculate apparent molecular weight of the gas. The four options are: option A 0.69, option B is 0.44, option C is 0.87, and option D is 0.79. Try to solve this numerical. The apparent molecular weight of the gas is already given, so you have to find the specific gravity of the gas. Write down the question first and then try to solve the numerical. Yes, any question? If you have any question, you can unmute yourself and ask me. First, you try from your side. If you are not able to solve it, I will anyway solve it. Okay, so let me solve this equation. Anyone, any answer? Anyone have solved this equation? It's very easy. I have already given you the formula, the for the specific gravity. Anyway, let me just. So the apparent molecular weight is given as 20, and the flow rate is given as 1.5 mmscf per day. So to find the specific gravity of gas, the formula is apparent molecular weight divided by the molecular weight of air. I have already told you the molecular weight of air is 28.97, and the apparent molecular weight is given here already, that is 20. So if we solve this, the answer should come out as 0.69. The gas flow rate is here just given just to create some confusion. You should remember the formulas and understand the question correctly, what the question is asking. So for the specific gravity of gas, the formula is apparent molecular weight by molecular weight of air, and we have to remember this, that molecular weight of air is 28.97, and apparent molecular weight of air of the gas is already given, which is 20. So 20 by 28.97 is 0.69. So this was a very easy numerical. And okay, write down the numerical, then we can proceed to the next question. If you have any doubt, you can ask me. You can unmute yourself and ask me.
Hello, sir.
Yeah, hello.
Assalamu alaikum, sir. Sir, if you don't mind, sir, I think if you solve a question first, then it will be more effective than this.
Which question?
I mean, for every question, if you solve first on your own,
Okay.
like
Actually, see,
this.
I this is the for first for some time there are people who wants to maybe try the numerical from their side. So I just give a 5 to 7 minutes for you people to try once. If not, I will anyway solve the numerical. If I directly give the solution, so it becomes means people doesn't want to try much. You can understand that, right?
Okay, sir.
Okay. Don't worry, I will anyway solve the numericals just for 5 minutes, for 3 minutes. is given to you just for yourself to, because I have already given the formulas. You can just try, or you can get any answer. It's not necessary that you have to give me the correct answer also, but I just want you people to try from yourself once, because these are very simple numericals. And
Yes, sir.
so if not, I will anyway solve it.
Okay, sir. Thank you.
Also, you have to carry on a 2 hour class. So if I keep on solving in the, it will get over in only 1 hour only. So yes, write down this and then we'll go to the next question. We'll be going slowly only. So if there is any question, any problem, you can ask me directly. You can unmute yourself and ask me. You can discuss anything, any other doubt also from the class also if you have any doubt.
Sir, in the question, it was written as calculate the apparent molecular weight. So I think it was wrong. We have to calculate specific gravity, right?
Yes, the a gas well is, let me tell you the question again. A gas well is producing gas with apparent molecular weight of 20. The apparent molecular weight is also already given as 20, and it is the gas is flowing at a rate of 1.5 mmscf per day, and we have to calculate the apparent molecular weight of the gas. The four options that are given as are 0.69, 0.44, 0.87, and 0.79. You can write
No,
down the
sir. My question
yeah.
is at the end. It is written as calculate apparent molecular weight. So, but we calculated
Okay, okay.
specific
So yeah,
gravity.
no, no, you are correct, correct. Yeah, it's a mistake here. Let me just correct it, because
Yes,
apparent
sir.
molecular weight is already given. And
Yes, sir. Yeah.
thank you for pointing this out.
Okay, sir.
Okay, so you have to calculate the specific gravity of the gas. Correct the question, and then we can go back to the next question. Go to the next question. Okay, so let's go to the next question. Determine the initial gas in place in mmscf, million metric standard cubic feet, from the given data. The area is given as 2000, it will be feet cube. Height is given as 50 feet. Average porosity is 0.18. Gas expansion factor is 175.44 SCF per feet cube. Gas saturation is 0.20, and the options are option A 24056 mmscf per day mmscf, option B is 27512, option C is 15603, and option D is 43256. Write down the question and try to solve it. I will give you 5 minutes.
Excuse me, sir. Sir,
Yeah.
will you upload this session today, if possible?
Let's see if I can upload today, because
Okay, sir.
class will already get over at 9, so it becomes very difficult to upload it on the same day, because uploading takes another 1 hour to 2 hours.
Okay, okay, sir.
Tell your friends and all to join this live session, so it will be easier for you people also, because sometimes it gets delayed in uploading of these videos in YouTube and the solutions, because first class was little bit theoretical. From now onwards it will be maximum numericals we will be doing. And also will be, if there is any doubt with the concept, if there is any doubt with your class, you can discuss it here. So yeah, for better understanding of the course, it is better if you people join the live session. Okay, so try this numerical from your side once, then I will be solving it, giving you 5 minutes for that, 5 to 6 minutes. Okay, so let me solve this numerical. So what are the data given? Area equal to 1000 feet. Height is given as 50 feet. Porosity is given as average porosity is 0.18. Then gas saturation is 0.20, and gas expansion factor is given. It is given as 175.44 SCF per feet cube. SCF per feet cube. So first you have to find the gas formation volume factor. This is, I have already told you, that is 1 by Eg, gas expansion factor, that is 1 by 175.44. So the unit will be now feet cube per SCF, and it will be how much it is coming out. It is coming out as 0.0057 feet cube per SCF. So the gas formation volume factor is 0.0057 feet cube per SCF. Now to find the initial gas in place, the formula is, I have already given you the formula. It is 43560, then AH5SG divided by DG. So it will be 43560. It will, area will be 2000 into height, how much, 50, and the porosity is 0.18. And let me do one thing, let me just erase this part, write it in the next line. So it will be 43560, 2000 into 50 into 0.18 into 0.20 divided by dg. How much you find? 0057. So if we calculate this, let me calculate this. If we calculate this, the answer should come out as 27511.799 mm SCF. So it will be 27512 mm SCF. Okay, so write down this numerical, and after that we can go to the next question. If you have any doubt, you can ask me. Sorry for the there was a my PC got disconnected. Sorry for the inconvenience. So okay, so let us start. Can you see the slides? Can anyone please unmute and let me know? Can you see the slides now?
Hi, sir. I can see absolutely, sir.
Okay, so we have already noted down the question. So here is the solution. Just write the solution. From here we will be going here. So write down the solution, and after that we can go to the next question. Let me know once you have done. Once you are done writing this numerical, and then we can shift to the next question. This one of the this a very important numerical actually. These type of questions are often asked in GATE. If anyone is interested in giving GATE in petroleum engineering, so you should be aware of this type of questions. Also, you have to be very careful about the units used in the question and the units you are using for solving the numericals. Many students that do the mistake of not noticing the units, not noting down the units properly. So don't do that. So okay, the correct answer is 27,512 mmSCF. That will be 27 option B. Let me go to the next question. Question 3. If the reservoir temperature falls in between the critical temperature Tc and the Crickondon thumb temperature Tct of the reservoir, then the reservoir is classified as option A black oil reservoir, option B retrograde condensate reservoir, now option C near critical crude oil reservoir, and option D volatile crude oil reservoir. Any any guesses? If the temperature is between the critical temperature and the Crickondon thumb temperature of the reservoir, then the reservoir is classified as black oil reservoir, retrograde gas condensate reservoir, near critical oil reservoir, volatile oil reservoir. Okay, the answer is retrograde condensate gas condensate reservoir, option B. So write down, then we'll go to the next question. Okay, next we'll go to the next question. Question 4. The condition at which the bubble point pressure curve meets the retrograde dew point pressure curve for any reservoir fluid is called. Option 1 is, here it is already. Option 1 is saturation pressure. Option B is retrograde pressure. Option C is critical pressure, and option D is dew point pressure. The condition at which bubble point pressure curve meets the retrograde dew point pressure curve for any reservoir fluid is called option A saturation pressure, option B retrograde pressure, option C critical pressure, and option D dew point pressure. So the correct answer is option C critical pressure. So write down, then we can go to the write down the question and the solution, then we can go to the next question. See, it's better if you attend the classes because some of the questions will be repeated in your this year's assignment also. So at least if you do the numericals, you will get an idea how to solve this year questions. And you can also ask me some doubt related to this year questions also if you have any doubt. But before that, you have to solve previous year questions and previous year assignments. Okay, let's go to the next question. Question 5. During production, the low shrinkage oil has a gas oil ratio of option A more than 3000 SCF per STB, option B 2000 to 3000 SCF per STB, option C 200 to 700 SCF per STB, and option D less than 200 SCF per STB. During production, the low shrinkage oil has a gas oil ratio of option A more than 3000 SCF per STB, option B 2000 to 3000 SCF per STB, option C 200 to 700 SCF per STB, and option D less than 200 SCF per STB. Try to get an answer for this, and we'll also take a 5-minute break here so that you can rest and we can continue the class after 5 to 6 minutes.
Sir, I think less than 200 SCF per STB.
Okay, so you're saying the less than 200 SCF per STB. Okay, let's see, let others try if anyone else want to give the answer. Also, you can everyone can take a 5-minute break. I will be coming after 5 minutes. Okay, so let us resume. Yes, you are right. The option is option D, that is less than 200 SCF per STB. Okay, so let us go to the next question. Calculate the specific gravity and density of 35-degree API crude oil at standard conditions. Option A 0.84 in and 52.9 lb per feet cube. Option B 0.72 and 47.8 lb per feet cube. Option C 0.92 and 60.7 lb per feet cube. And option D 0.66 and 41.4 lb per feet cube. So try this numerical. So okay, so let me solve this numerical. First, we have to calculate the specific gravity and then the density. The API gravity is given. The four options are option A 0.84 and 52.9 lb per feet cube. Option B is 0.72 and 47.8 lb per feet cube. Option C is 0.92 and 60.7 lb per feet cube. And option D is 0.66 and 41.4 lb per feet cube. These are the four options. So let me go to the degree API is given as 35. So I have already given you the formula. API equal to 141.5 specific gravity of oil minus 131.5. So it will be 35 equal to 141.5 divided by specific gravity of oil minus 131.5. So if we solve this, can anyone solve and tell me the answer? So if we solve this, the answer should be 0.849. This is the specific gravity of the oil. Next, we have to find the density of the oil. So the formula is the specific gravity for finding the density of the oil when specific gravity is given is very simple. It will be 0.8. Let me write down the formula first. Okay, so let me write down the formula. This density of oil so equal to specific gravity of oil into 62.4. What is 62.4? It is the density of water in lb per 62.4 lb per feet cube. It is the density of water in lb per feet cube. So to find the density of oil, we just have to multiply the specific gravity of oil with the density of water at standard pressure temperature, which is, if we multiply these two, the answer should be 52.9 lb per feet cube. So write down this, then we'll go to the next numerical. If we have written the numerical, then we can go to the next question. So the answer for our question will be, correct option will be option A, 0.84 and 52.9 lb per feet cube. So let me go to the next question. A gas well is producing at a rate of 17,000 feet cube per day from a gas reservoir at an average pressure of 2000 psi and a temperature of 240 degree Fahrenheit. The apparent molecular weight of the gas produced is 40. Calculate the viscosity of the gas in Cp at 1 atmosphere, considering only hydrocarbon gases are produced from the well. Option 1 is 0.0102, option 2 is 0.0112, option C is 0.0108, and option D is 0.0104. Write down the question. For solving this question, we'll be using the graph. There is a graph given to us. Here you can see this. Can you see the these lines? Can you see the arrow where I am pointing? These are the lines depicting the reservoir temperature. So our reservoir is somewhere between 200 degree Fahrenheit and 300 degree Fahrenheit, because it is given here 240 degree Fahrenheit. So, and also the molecular weight of the gas is also given. The molecular weight of gas is given as 40. You can see the x-axis here. It is the molecular weight of the gas. You can see if 40 is marked in the x-axis, and 240 degree is marked on this curved lines, 240 degree Fahrenheit. So from this we can find out the viscosity of the gas. Can anyone use this and tell me what will be the viscosity of the gas? So when we will be using this, then our sorry. So our answer will be lying somewhere here between 0.010 and 0.011. I don't know how much it is visible to you, but as this question was in a previous assignment, so I am explaining it here. See, you have to use this graph. use this graph for the temperature. The curved lines are given for temperature and the molecular weight is given on the x-axis. On the y-axis, the viscosity is given. So for us, the molecular weight is 40 and the temperature is 240. So if you intersect these two lines and see on the y-axis, our answer will be somewhat 0.108. So the correct answer is option C, 0.108. So
Excuse me, sir.
yeah,
Sir, is that somehow related to we used to find a wet bulb and dry bulb temperature in its mass transfer. Is this similar to this graph?
what you are saying? Can you just repeat once again?
Sir, in our last semester, there was subject mass transfer, sir.
Okay. Yeah.
Um,
You can
there
relate.
was
Yes, in mass
similar
transfer you
graph
have
like this.
similar type of graphs. Yes.
We used to find a wet bulb and dry bulb temperature in that.
Okay. Yeah, you can relate to this graph. These graphs look very complicated. But if you see in the question they ask in GATE or in petroleum engineering, they ask very simple question. Like this question also, they have already given the molecular weight in the x-axis. The temperature is given in the curved lines. You just need to intersect these two lines and then see where does the line intersect the y-axis. Wherever the line intersect the y-axis, that is your viscosity. So yes, you can relate to your mass transfer and similar type of graphs are there in mass transfer also. Yeah. So okay, we can go to the next question because there is nothing much here to elaborate and you can note down this graph also because it will be very complicated. But but please understand the procedure because in this year assignment also you will be getting this type of questions and you have to solve by comparing these values on the x-axis and on the curved lines. Next question is which of the following tests can be used for determination of methane in natural gas? Option A is swelling test. Option B is gas chromatography. Option C is special laboratory PVT test. Option D is slim tube test. Which of the following tests can be used for determination of methane in natural gas? Option A swelling test. Option B gas chromatography. Option C special laboratory PVT test. And option D is slim tube test. Any guesses?
Sir, option B.
Option B. Yeah, in option B. Anyone else? Yes, the correct option is, you are absolutely right. The correct option is option B. So, okay, so this is the answer of the eighth question. Which of the following tests can be used for determination of methane in natural gas? The answer is gas chromatography. So let me go to the next question. Before going, let me tell you. So see, these uh, videos may be recorded, may be uploaded in the YouTube. You may get the session, but when you are attending the live classes, that will be little beneficial for you because here you can ask me anything. Again, if you are watching these live videos, it's just like watching the NPTEL videos. There is no interaction. There is no process of solving the doubt. If you are having any doubt in the subject, if you are, I know this subject, all of you are from mainly from chemical engineering background, and this subject is very new to you. But if you want any basic question, means if you are asking me what is the porosity, what do you understand by permeability, or any what do you mean by reservoir, if you ask me, That also I can explain, because I know you are from a different background and you don't have so much knowledge about petroleum engineering. So attending the live questions, you can ask me any doubt, any query, and we can discuss it in the class, which will not be available when you are going through the YouTube videos. You can solve the assignments maybe by looking at the videos, but in live session you can clear your concepts that won't be easily means done when you are attending a recording video. So the people who are present here, I am asking you to tell your batchmates also, those who have enrolled in this class, to please attend the live sessions. If there are more people, then we also get more interest, and we also want to do some little bit complicated numericals for you people, so that if you are applying for the means, when I am preparing these numericals, I always keep in mind the gate point of view. So if the attendance is more, then I can solve little bit of gate questions also. That will be, because nowadays you can give gate into two subjects. So you can opt for chemical engineering and also opt for petroleum engineering. And for petroleum engineering, the rush is not like chemical engineering, mind you. For petroleum engineering, you can get a good score and you can get a admission in any good IITs for PhD, for masters, and also you can opt for PSU also. There are PSUs like ONGC, IOCL, they take from petroleum means people from through GATE petroleum engineering. So it will be very helpful to you if you attend the live session rather than just seeing the recorded videos and solving the assignments. So okay, this is just a little bit of discussion what I want to convey you. So let us go to the questions again. There are two more questions we'll be solving today. Both of them are numerical. So for both the question 9 and question 10, the question is same, and we have divided in two parts. The question is, a gas well is producing at a rate of 15,000 feet cube per day from a gas reservoir at an average pressure of 4,000 psi and a temperature of 150 degree Fahrenheit. Determine the gas solubility in water and the water isothermal compressibility. Let me repeat the question. A gas well is producing at a rate of 15,000 feet cube per day from a gas reservoir at an average pressure of 4,000 psi and a temperature of 150 degree Fahrenheit. Determine the gas solubility in water and the water isothermal compressibility. Write down the question. We have to find two things here. First, the gas solubility in water, and next is the water isothermal compressibility. So, for calculating the gas solubility in water, there are four options. Option A is 46, option B is 50, option C is 60, and option D is 40. The four options are: option A is 46, option B is 50, option C is 60, and option D is 40. Write down the question. Write down the question and try from your end. Then I will solve the. I will give you 5 minutes for so that you can try from your end. Then I will solve the numeric. Okay, so let me solve this numerical. So this numerical is little bit different from others. So for this is based on a, what is this called, formula given by one of the scientists. Yes, solubility in water. ISW equal to A plus B E plus CP square. CP squared. So where A equal to 2.12 plus 3.45 10 to the power minus 3 into temperature T minus 3.59 into 10 to the power minus 5 into T square. For B it is equal to 0.017107 plus nice actually, minus just give me 1 second, minus 5.26 10 to the power minus 5 into 150 minus 5 into T plus 1.48 into 10 to the power minus 7 into T square. For C it is equal to 8.75 10 to the power minus 7 plus 3.9 10 to the power minus 9 into T minus 1.02 10 to the power minus 11 into T square. These are the formulas for finding A, B, C. So now we'll be finding the value of A. We have 2.12 plus 3.45 10 to the power minus 3 into temperature is given as 150 minus 3.59 into 10 to the power minus 5 into 150 square. So if we calculate this, the answer should come out as 1 point answer should come out as 1.82975. Next, for B, the formula is 0.0107 minus 5.26 into 10 to the power minus 5 into 150 plus 1.48 into 10 to the power minus 7 into 150 square. So if we solve this, the answer will be coming out as 0.00614. So let me go to the next slide. So the for C it is equal to C equal to 8.75 10 to the power minus 7 plus 3.9 10 to the power minus 9 into 150 minus 1.02 into 10 to the power minus 11 into 150 square. So if you solve this, the answer should come out as 1.2305 into 10 to the power minus 6. So so to find the RSW, solution of gas in water, it is A plus BP plus CP square. So it is 1.82975 plus 0.00614 into 4000. The pressure is given as 4000 plus 1.2305 into 10 to the power minus 6 into 4000 square. So if you solve this, the answer should come out as 46.0775. So this is your ultimate answer. So this numeric is a little bit lengthy. So first you copy down this slide, then I will, after 5 minutes, I will go to the next slide. Copy down this one, then we will go to the next slide. Okay, so I hope you have written down the first slide. So this is the next slide. Write it down, then we can go to the final question for today. Okay, so the answer is 46. That is the first option. Let me go to the last question for today. So calculate the water isothermal compressibility. The four options given are option A 3.8 into 10 to the power minus 6, 1.8 into 10 to the power minus 6. Option C is 5.8 into 10 to the power minus 6, and option D is 2.8 into 10 to the power minus 6. Calculate the water isothermal compressibility. Option A 3.8 into 10 to the power minus 6. Option B 1.8 into 10 to the power minus 6. Option C 5.8 into 10 to the power minus 6. And option D is 2.8 into 10 to the power minus 6. So write down the question, then we will go to the solution. This question is also,
Hello, sir.
yeah, hello.
Okay, sir. Sir, can you just explain in 1 minute the graph which you explained?
Okay, okay, the previous
How
graph.
we. Yes, sir. Just in 1 or 2 minutes.
Okay, so yeah, you can see in the here, first see the question what they are asking. They have asked the question: a gas well is producing at a rate of 17,000 feet cube per day from a gas reservoir at an average pressure of 2000 psi and a temperature of 240 degree Fahrenheit. The temperature is given as 240 degree Fahrenheit. The apparent molecular weight of the gas is 40. Calculate the viscosity of the gas in Cp at 1 atm, considering only hydrocarbon gases are produced from the oil. They have told us to calculate the viscosity of the gas, considering only hydrocarbon gases are produced from the well. The graph that is given, it is only for hydrocarbon gas. So the temperature is given as 240 and the molecular weight of the gas is 40. You can see here in the graph. Can you see it properly?
Yes, sir.
Yeah, let me just. Can you see it properly now?
Yes, sir. On x-axis. Yes, sir. On x-axis, it's molecular weight, and on y-axis, viscosity.
Yeah, y-axis, and you can see the middle curved lines: 100 degree Fahrenheit, 200 degree Fahrenheit, 300 Fahrenheit, 400 Fahrenheit.
Okay. Okay, sir.
You can see those, right?
Yes, sir.
Okay, so
Temperature lines.
yeah, the molecular weight is 40. So you first go to 40 on the x-axis, then go straight up. You can see my arrow.
Yes, sir.
Yeah, at 40 you go straight up to the temperature of 240. See it, you can see this one is for 200.
Okay, sir. But sir, molecular weight 40 is just right away. You are between 10 and 20.
Okay, so this is due to some lag in my system, lag maybe. Now you can see my arrow
Yeah.
is on 40.
Yes, sir.
And see,
Sir, it is between 10 and 20 molecular weight. I think due to lag of
okay, due to lag,
connection.
you just go for from 40.
Okay.
You got go straight
Yes, sir.
up to this
Right.
temperature. You can see 200 temperature. After that, this one is 220, 220, 240,
Ye-
260. Yeah, there is, yeah,
Okay, sir.
after 200, the next line is for 240, 220. Then the next line is for 240. So you first have to combine this 40 with this 240 curved line where it is going.
Right, sir.
Okay, so it is maybe somewhere here. Okay, then you can
Okay, sir.
go to the left side, and your point will be somewhere here between 0.010 and 0.011. Understood?
Okay, sir. Understand. Understand.
Okay,
Understand, sir.
okay,
Thank you, sir.
welcome. So okay, let me solve the last question of the day. This is also based on correlations. So let me write the formula first. It's CW equal to C1 plus C2T plus C3T square, whole thing into 10 to the power minus 6. So for finding the for finding C1, the formula is 3.8546 minus 0.0000134p. So it will be 3.8546 minus 0.0000134 into pressure is given as 4000. So it will be C1 value will be 3.3186. Next we have to find C2. For finding the C2, the formula is minus 0.00 minus 0. Just 10 0.0 minus 0.0105 1052 plus 4.77 into 10 to the power minus 7 p. So if we calculate this, it will be 0.01052 plus 4.77 into 10 to the power minus 7 into 4000. So the answer should come out as minus 0.008612. For C3, the formula is 3.9267, 3.9267 into 10 to the power minus 5 minus 8.8 into 10 to the power minus 10 pressure. So it will be 3.9267 into 10 to the power minus 5 minus 8.8 into 10 to the power minus 10 into 4000. So the answer will be for this, it will be 0.0003574. So if you calculate all this, the CW should come out as C1 is 3.31318 plus minus 0.00 0.008612 into 150 plus 0.0003574 into 150 square and into 10 to the power minus 6. So the final answer that should come, it is as 2.8. So answer should come out as 2.83 into 10 to the power minus 6. So this is your answer. So write down, and after that we'll end today's class. So the correct option is 2.8 10 to the power, that is option D. Okay, so hopefully you have written the numerical. So thank you. We'll see you in the next class, and hopefully the attendance will be little more in the next class. And those who are present in today's class, I request you to tell other people to attend the class. So no matter how much you see the video recording, but this interactive class is made for a reason, so that you can clear all your doubt related to, not just related to the numericals, to the related to the course also. Okay, thank you. Take care. See you next Tuesday.
Thank you, sir.